We're going to start section 3.3, linear independence. Suppose we have a vector space, V, and let's have these vectors v1 through vn in our vector space. We say that these vectors v1 through vn are linearly independent if c1 v1 plus c2 v2 all the way to cn vn is equal to 0 if and only if c1, c2, all the way to cn is equal to 0. So this is saying the only time we can have a linear combination of these vectors equaling the 0 vector is when every one of these coefficients, these scalars, is equal to 0. The vectors v1 through vn are called linearly dependent if c1 v1 plus c2 v2 all the way to cn vn is equal to 0 if and only if some ci are not equal to 0. So when we have a linear combination of these vectors and we get the 0 vector, plugging in 0 for each one will give us the 0 vector if we plug in 0 for these scalars, but also we can plug in at least one non-zero number for one of these c's and still get the 0 vector. Let's look at an example. Here I have two vectors in R2, and I want to know if they're linearly independent. So what I'm asking is, can you find a C1 and a C2 that are non-zero, or at least one of them is non-zero, that when you sum these two together, you get the 0 vector? So this is the same thing as asking, what are the solutions to this system? So to find the solutions, we're going to make an augmented matrix. We're going to put 1, 2, 1, 9 here, 0, 0, and let's find the solutions. So I'm going to put this in reduced row echelon form. So I'm going to subtract row 1 from row 2. And I get 1, 2, 0, 0, 7, 0, and then divide the second row by 7. And then we're going to multiply, we're going to get rid of this 2 as well. So this is the reduced row echelon form, which tells us that C1 is 0 and C2 is 0. So there is not a C1 or a C2 that's non-zero that satisfies that this vector plus this vector is equal to the 0 vector. So when you can only find that you get the trivial solution, C1 is 0, C2 is 0, then these two vectors are linearly independent. So the answer to the question is yes, they're linearly independent. Let's look at an example where they're not linearly independent. So they're linearly dependent. Are these vectors linearly independent? So we can do exactly the same thing we did before. We can say, can we find a C1 and a C2, where at least one of them is not 0, to give us the 0 vector? And you can put this exactly like we did last time into an augmented matrix and put it in reduced row echelon form. and see what you get, and you can find C1 and C2. But you can also notice just by looking at these, 1, 2, let's put this in red here. 1, 2, if I multiply that by 2, that gives me 2, 4. So I can just subtract 2, 4, and I'll get 2, 1, 2, minus 1, 2, 4. That gives me the 0 vector. So I get a non-zero solution for C1 and for C2. So C1 is equal to 2, and C2 is equal to negative 1. So here I have this C1 not being 0 and this C2 not being 0, and we get something that's 0. So exactly what you think linearly dependent means, one of the vectors is dependent on the other vector. So here you can see that this 1, 2 or 2, 4, it doesn't matter which one you say, these depend on each other. So these vectors are not linearly independent. Now you could continue finding the reduced row echelon form of this. Let's do that as well to see what we get. So I'm going to erase this just so we have this option as well. We'll get 1, 2, 0, 0, 0, 0, and you see that C1 is equal to negative 2 C2, and you see that you have infinitely many solutions. So not just the 0 vector works. Now the 0 vector is one of the solutions. So if we put 0 in for C1 and 0 in for C2, we do get this, 0, 0. But now we're also saying that we can put things that are non-zero in for C2, and that will determine something that's non-zero for C1, and that also gives us the 0 vector. Let's look at one that's a little more complicated. Are these vectors linearly independent? So what we need to do is see if there is a C1, a C2, and a C3 that when we add these vectors together, we get the 4 by 1 0 vector. So what we're trying to figure out is if one of these vectors is a linear combination of the other two. Well, this one's kind of hard to see. The last one, you could definitely tell that you just multiply one of the vectors by 2 and you get the other vector. So here I would definitely put this in a matrix. So you want to put these columns as columns of your augmented matrix. So you have 1, negative 1, 2, 3, negative 2, 3, 1, negative 2, 1, 0, 7, 7, zero, 0, 0, 0, and then put this into reduced row echelon form. I'm going to skip that. You can do it as an exercise. In row echelon form, you should get something that looks like this. And now in reduced row echelon form, you'll get 1, 0, 3, 0, 1, 1. These are rows of zeros. And we see that C1 is equal to negative 3 C3, and C2 is equal to negative C3. And C3 is a free variable. So if we choose C3 to not equal 0, let's say C3 is 1, then C1 is -3 and C2 is -1, and that should be a solution. So let's see if we can plug this in. So we said C3 is 1, so I'm going to put a 1 here. C2 is -1 and C3 is -3. And let's just see what we get. So we have, for the first entry, we'll have -3 plus 2 plus 1, and that is 0, which is what we get here. Okay. What about for the second entry? So we'll get a +3, because -3 and -1, and then we'll get a -3, and then +0. So we get 0. And continue this. You'll get 6, a -6, a -7, and then a +7. That's 0. And then -9, 8's -7, and then +7. That is also 0. So you can see you get that C1, C2, C3, not all of them are 0. You could have one of them being 0. That would be fine. But as long as one of them is not 0, then the vectors are linearly dependent. So the answer here is no. They're linearly dependent. And think about what the word dependent means. That means one of these vectors depends on the other ones. And you can see that. You could move this, if we plug in this -3 and this -1 in, you can see that if we move these to the other side, we add the 0 vector to them, what we're going to get is 3 times this one plus 1 times this one is a linear combination, and that if we add those together, we'll get this vector. So you can see that this vector depends on these two. That's another way to think about linearly dependent vectors. You can write one of the vectors as a combination of the other vectors. So I want you to notice also with this problem what I did to solve it. So we had a C1, C2, and a C3. And we noticed that this was a system. And this system, we make a matrix A, and we multiply it by x and get 0. Where the system, where we may have this matrix A, that consists of these vectors here. So A is V1, V2, V3. Where this vector here is V1, this vector is V2, and this vector is V3. And this C1, C2, C3, that corresponds to x. X is equal to C1, C2, C3. So what we're doing is we're trying to find all the solutions to A times x is equal to 0. So in other words, we're trying to find the null space of this matrix here. So what does it mean when the vectors are linearly independent? Well, if they're linearly independent, the only solution is the 0 vector. And if that's the only solution, that would be the only x vector here, which would tell us that the null space is equal to 0, just the 0 vector, when the vectors are linearly independent. So let's write this here. The vectors v1, v2, v3 are linearly independent if and only if the null space of our matrix A is equal to the 0 vector. Now the null space is always going to have at least one vector in it, and that vector being 0, because 0 is always a solution to A times x is equal to 0. But it could have more. And if you have more than one vector, then if you find that the null space you will find that the null space will have more than one vector. So it won't just include the 0 vector. So linearly dependent means it'll be bigger than just the 0 vector. The null space will be bigger.